Yo, yo, yo. Hi. Hola. Hope everyone's having a good day. We'll wait about 30 more seconds and then I'll get started. It's supposed to be cooler today, isn't it? Let's see. Ooh, only 75 today. That's nice. All right. Well, the number of concurrent viewers keeps going down, so I'm just going to get started. All right. So the lesson that I pre-recorded, which I hope went okay for you guys. The lesson that I pre-recorded was about momentum. Okay. And so we're going to continue with momentum. Today's lesson is about two things. The first topic is two-dimensional collisions. All right. So it's really an extension of what I talked about in the last lesson. So let's see how that works. We've got a let's say a 2 kilogram object that is moving this way at 10 meters per second. And then we have a 3 kilogram object that is moving this way at 5 meters per second. Okay? And that angle right there is 30 degrees. So these two are going to collide. Okay, they'll have a collision right about there. We're assuming that all the distances are worked out so that they actually have a collision. Because as it looks like this one would probably go down first. So they have a collision right there. And then they collide and they stick together. So they have a completely inelastic collision and they go somewhere. And what we want to know is what is the final velocity vector, okay, of this pair once they stick together. All right? So the first thing we want to do in a two-dimensional collision problem is we want to write the momenta in terms of in IJ form, okay? So I know that the magnitude of this momentum, so remember momentum is mass times velocity. So the magnitude of this momentum is going to be 20 kilogram meters per second. The magnitude of this momentum is going to be 15 kilogram meters per second, okay? But I got to put the directions in because these are vectors. Well, this one is going downward. So this one has a momentum vector in the negative j direction. So that's going to be minus 20j kilogram meters per second. All right. This one, we know it has a momentum of 15, and we know that this angle is 30 degrees. So we can use trigonometry to figure out the I and j components. So this one would be 15 sine of 30, which is 7.5. And this one would be 15 cosine of 30, which is about 13 meters per second, or kilogram meters per second. Okay? So this particle's momentum is going upward at 7.5 and across at 13. So 13I plus 7.5 J kilogram meters per second. Okay? So what that says, so now we know the momenta of the individual particles. So really the only extra stuff you need to do is you need to figure out the I and the J components. So that means that our total initial momentum is 13I plus 7.5 J. So that's the first one, plus negative 20 J. So we have to do this vector addition. So I subtract 20 from 7.5, and I get 13I hat minus 12.5 J hat kilogram meters per second. Okay? So that is my initial momentum vector. Now, as we learned last time, momentum is always conserved in collisions. So the total initial momentum has got to be equal to the total final momentum. Okay? Total initial momentum has to be equal to the total final momentum. Now, just like with completely inelastic collisions in one dimension, in two dimensions, the final momentum, we basically just combine the two masses to get a mass of 5, and the final velocity we're going to calculate. So I just leave it as a vector variable. Okay. The initial momentum is 13I hat minus 12.5 J hat. So I divide both sides by 5, and so that's going to give me 13 divided by 5 is 2.6. So 2.6 I hat minus 12.5 divided by 5, which is going to be 2.5 J hat. So this is our final velocity vector. Okay? So we know that when these collide, they're actually going to be headed to the right, and they're going to be going downward. One of the things I might ask, instead of what is the final velocity vector, I might ask what is the final speed of the pair once they collide. Okay? All right? And so in that case, well, we know that this velocity, it goes over 2.6, and it goes down 2.5, okay? And the hypotenuse is going to be the speed. So to get that speed, I could do the Pythagorean theorem, do square root of 2.6 squared plus 2.5 squared. And that gives me about 3.6 meters per second is the final speed of the pair. Okay? If you wanted the angle, what's the final angle? You could do, that final angle is going to be the inverse tangent of 2.5 over 2.6. Okay? It's going to be about 45 degrees because the two sides are equal. So like 45 degrees south of east. All right? So that's how you do two-dimensional collision problems. It's pretty straightforward. It's just an application of trigonometry. So that's the first part of my lesson. By the way, today's lesson is going to be pretty short and sweet. So for the next part, we've got, I want to talk about what are called elastic collisions. Okay? Actually, I'm going to talk about one-dimensional elastic collisions. Okay? So a one-dimensional elastic collision is, so that phrase, an elastic collision, means that none of the initial kinetic energy is converted to other forms. Okay? So normally what happens when two things collide is that some of that energy will become heat, or it will become sound, or it will go into deforming the objects or something like that. But if you have an elastic collision, then whatever kinetic energy you started out with is the kinetic energy that the products of the collision will have. Okay? So only if it explicitly says this is an elastic collision, only if it says elastic collision, you can say that the initial kinetic energy is equal to final kinetic energy. Okay? Only if it says elastic collision. If it doesn't say that and you use this equation, you will get the problem wrong. Okay? A completely inelastic collision, the initial kinetic energy is not equal to the final kinetic energy. Actually, the initial kinetic energy is larger than the final kinetic energy because when they stick together, heat is generated. Okay? So you got to be really careful about that. All right, so let's do an example to see how this works. Okay? So let's just go with the same numbers as before. We've got the 3 kilogram object is moving this way at 5 meters per second. And then the 2 kilogram is moving this way at 10 meters per second. Okay? So this is before the collision. There's a question, if it doesn't say elastic or inelastic, do we just assume inelastic? Yes. Yes. You never assume that this is true unless it says elastic collision. Okay? I guess I get so like worked up about that just because I can literally remember sitting in my physics class when I was in high school and solving a problem, and I used this equation instead of initial momentum equals final momentum, and I got the question wrong, and like I was like really good in physics in high school, and I got so pissed that I got that wrong. I don't know, it's just stuck with me all these years. I can literally remember sitting in my desk and getting that problem wrong from like 20 years ago or something. You know, it's crazy. Okay. If you're wondering if I hold a grudge, yes, I do. So they have a collision in the middle here. Okay. And then afterwards, they have some final velocities. Okay. So this one has a velocity which I'll call V3. And this one has a final velocity which I will call V2. Okay? So first of all, let's write an expression for the initial momentum. The initial momentum is going to be 3 times 5. So that's the momentum of this one, plus 2 times negative 10. That's the momentum of this one. So that's 15 minus 20, negative 5 kilogram meters per second. Okay? The final momentum, we don't know what these velocities are, so we have to write an abstract expression for the final momentum. So it's going to be mv plus mv. So 3v3 plus 2v2. Okay. One important thing about this is I'm assuming that both velocities are positive. Okay, even though clearly this one is going to get bounced to the left, when you write your abstract equation, you write it from the perspective of assuming that everything is going to be positive. Okay. Now let's think about the kinetic energy. The initial kinetic energy is going to be 1/2 mv squared for the left thing plus 1/2 mv squared for the right thing. So 1/2 times 3 times 5 squared plus 1/2 times 2 times -10 squared. That negative is going to get squared away, so it's going to be two positive numbers added together. So this is 75 divided by 2, that's 37.5. This is 100. So these are going to add together to give 137.5 joules is the initial kinetic energy. For the final kinetic energy, we have to write an abstract expression. Okay? So it's going to be 1/2 times the mass of this one times the velocity of this one squared, so v3 squared, plus 1/2 times the mass of this one times the velocity of this one squared. Okay? So basically, after the collision, we have abstract expressions. Before the collision, we have concrete expressions. Okay? So now we set up our equations. One of our equations is going to be P initial equals P final. So that would be -5, because the initial momentum is -5, equals 3v3 plus 2v2, because that's the abstract expression for the final momentum. And then, because we have an elastic collision, only because we have an elastic collision, we can say that initial kinetic energy is equal to final kinetic energy. So we would have our initial kinetic energy was 137.5 joules, and our final kinetic energy is an abstract expression, 1.5 v3 squared plus v2 squared. So what do we have? We have a system of equations. We can actually solve for both of the final velocities of these masses. Okay? You could use substitution. You could solve for v3 in terms of v2, plug it in here, you get a quadratic equation. Let me tell you right now, doing the problem that way is very, very, very error prone. Okay? Even for me. Actually, when I wrote the quiz for this lesson, I spent like an hour just foiling numbers and getting an abstract expression, and it was just painful. It was so painful. I hated it. So for these problems, I would particularly recommend using Desmos. So let's see how that works. As I use Desmos, I'm going to let V3 be represented by Y, and I'm going to let V2 be represented by X. Okay? So let me switch over to Desmos. So first I'm going to write my momentum conservation equation. -5 equals 3 times Y plus 2 times X. So that is my momentum equation. It's a linear equation. Okay? It doesn't have any squares in it or cubes in it, so it's linear. My energy equation is 137.5 equals 1.5 y squared plus x squared. Now, if you remember from your math class, you know that equations of this type, where it's x squared plus y squared, ax squared plus by squared equals c squared, that's the equation of an ellipse. Okay? So the energy conservation equation is an ellipse. So really, what this problem boils down to geometrically, which I think is really neat, this problem boils down to the intersection of an ellipse with a line and finding where that intersection is. I think that's kind of a cool geometric interpretation. So we can see we actually have two intersections. We have an intersection right here, and that intersection has x equals -10 and y equals 5. So that would mean V3 equals 5 meters per second, and V2 equals -10 meters per second. So that's one solution, and we're going to figure out how to decide which of the two solutions is correct in a moment. For this one, the other solution says that V3 equals -7 meters per second, and V2 equals 8 meters per second. All right. So now we could go back. So I wrote this down. Now, if we look at our problem here, the 3 kilogram object starts out with a velocity of 5 meters per second. This one says V3 equals 5 meters per second. The 2 kilogram starts off with 10 meters per second to the left. That's a velocity of -10 meters per second. So we can see that this solution doesn't change the velocities, okay? This solution is the one where the two masses are headed towards each other and they miss each other. Because if they missed each other, kinetic energy is conserved and momentum is conserved, okay? So that is it's a valid solution, but it's not the one that we're looking for because they actually did hit each other. Their velocities did change from their initial values. So the correct solution is this one. And we can see that V3 is negative because it got bounced back. It gets bounced back in the opposite direction that it came from. V2 started out negative and it became positive because V2 got bounced back. Okay? So that's how you choose the solution. You kind of have to think about, well, one of these solutions is either unphysical or it's something that is just not what we were trying to calculate. Okay? I wasn't trying to calculate the scenario where these two are doing nothing. Okay? Cool. So we're going to do one more example. And this example is related to the previous one, but a little bit different. So I'm going to put this under the title of energy momentum problems. Okay, so let's do an example and we'll see how it works. So we've got a spring, okay. The spring is on a table. The table is frictionless. And this spring has a stiffness of 120 newtons per meter, and it is compressed by 1 meter. So it's compressed. It's ready to do its spring thing and go wow, 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 wow. Okay. On either side of the spring, we have a 1 kilogram mass, and we have a 2 kilogram mass. Okay, and these masses are initially at rest. Okay, the spring is allowed to decompress. it does its spring thing and goes wah, 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 wah. Okay, so now the spring is maybe like this. It decompresses, and the 2 kilogram mass gets sent off in this direction, so that's going to be called V2, and the 1 kilogram mass gets sent off in this direction, which I will call V1. And we want to know, what are the final velocities of these masses? Now, an important thing is that we're going to assume. We are going to assume all energy stored in the spring is transferred to the blocks. Okay? Which is not necessarily true. That's an assumption. Okay? What could happen is you could have a scenario where maybe the spring is compressed, it launches the block, and then afterwards the spring is going wow, wow, wow. If the spring is going like this afterwards, then that means it must have some kinetic energy still in it. Okay? So we're assuming that none of that, all of that energy, all of that initial elastic potential energy went into the blocks. Okay? So, so basically, one of our equations is going to be E initial equals E final. So the initial energy is all elastic potential energy. It's 1/2 kx squared, because there was no kinetic energy. Nothing was moving it first. And, oh my gosh, if you work that out, it's going to be 1/2 times k, which is 120, times x squared, so times 1 squared. So that is 60 joules is the initial energy. Okay? The final energy is all stored in the kinetic energy of the blocks. So it's going to be 1/2 m, which is 1, times v1 squared, plus 1/2 2 times v2 squared. All right? So that is the conservation of energy equation. Now we look at our conservation of momentum equation. So the initial momentum is 0 because nothing was moving. So we have, that's going to be 0 equals. And then after the spring decompresses, we have an abstract expression for the momenta in terms of the 2 kilogram and the 1 kilogram block. It's going to be 1 times v1 plus 2 times v2. All right. So again, this is an easier equation to solve, but it's still kind of tedious. So I will go to Desmos and I will type these in. I will have v2 being y, and I will have v1 being x. Okay, so I'm going to go over to Desmos. Okay, so I type in our energy equation. 60 equals 0.5 x squared plus y squared. So that's an ellipse again. And our other equation is 0 equals x plus 2y. So there's our two equations. We have a linear momentum conservation equation and a elliptical energy conservation equation. So let's see where the intersections are. So this intersection says that v1 is negative 8.9 meters per second, and V2 is 4.4 meters per second. Okay? This intersection over here says that V1 equals plus 8.9 meters per second, and V2 equals negative 4.4 meters per second. All right? So those are our solutions coming from Desmos. So how do we know which one to choose? Well, the thing you want to notice here is that these solutions are the same. They're just multiplied by -1. So we have negative 8.9 and plus 4.4, or plus 8.9 and negative 4.4. All right? And the thing is it depends on your perspective. So the way I've drawn this problem, V2, the 2 kilogram block gets launched to the right. So that means that the 2 kilogram block should end up with a positive velocity. Similarly, the 1 kilogram block should end up with a negative velocity because it's getting launched to the left. So that means that the correct solution is this one, from the perspective of this. But, if I'm viewing the piece of paper like this, I see the 2 kilogram going to the right. But what if I was looking at this problem from the other side of the piece of paper? Then from this perspective, think about it. If I'm holding my piece of paper like this, the 2 kilogram is headed towards you, okay? So from my perspective over here, the 2 kilogram went towards you guys, which is to my right, okay? If I look at it from this perspective, the 2 kilogram got sent towards you, but now from this perspective, it's to the left, okay? So it's giving us both, the mathematics is giving us both solutions, the solution from both perspectives, and we just kind of have to choose one based on whatever perspective we set it up with, okay? So I actually think that's really cool. This is kind of a situation where both are correct, okay? So yeah. Anyways, that is my lesson for today, and I will see you in the Zoom room. Bye for now.